Let's begin Chapter 9 by discussing the enthalpy of reaction, abbreviated as delta HR. Now in the book, you'll see delta HR also referred to as the heat of reaction. So it's also known as heat of reaction. But of course, we know that this is somewhat of a misleading name, because according to the energy balance, delta H doesn't have to be equal to Q. It depends on what the other terms in the energy balance are. And so, at least for this course, I'm going to just refer to it as the enthalpy of reaction, or just delta H of R. In any case, so as I mentioned in the introduction video, delta H of R is basically the net energy transfer between the amount of energy that's put into the system to break the bonds of the reactants and the energy that's released when the product bonds are formed. And so to give a formal definition, I'll just write here that delta H of R is the enthalpy difference when a stoichiometric quantity or quantities of reactants and at some temperature and pressure react completely. And completely is a key word here, so I'm going to underline it. And so when these things react completely and the resulting products that form are also at the same temperature and pressure, at the same T and P. Okay? And so this is the formal definition of what the enthalpy of reaction is. To at least give you a sort of concrete idea of what delta H of R is describing, I'm going to take you through some example reactions. And so, for example, let's start with this reaction. And so I'll call this reaction 1. And reaction 1 is going to describe the combustion of methane with oxygen. And so for this reaction, what we're going to do is we're going to start with 1 mole of methane, so CH4, and it's going to be a gas. And we're going to say that that methane reacts with 2 moles of oxygen gas. And when these things react together, they yield 1 mole of carbon dioxide as a gas and 2 moles of water, liquid water. Okay? And let's say this reaction takes place at 25 degrees Celsius and a pressure of 1 atmosphere. When this reaction occurs at these conditions, and if you measured the energy released from the reaction, you would see that the enthalpy reaction at this temperature and at this pressure would correspond to negative 890.3 kilojoules. Okay? And so we're just going to say that the delta H of R for this reaction number 1 is equal to about negative 900 kilojoules. Now there's a couple of things I want to point out here. The first thing I want to point out are the units. So I wrote here that the delta H of R is in units of kilojoules. But this is a bit kind of tricky, because the way that it's written in the book, it's written in kilojoules, but what it's really implying is that the delta H of R has units of kilojoules per mole of things that react. Okay? So I'll write this out here. So I'll make sure to draw attention, so pay attention to this unit, because it's actually per stoichiometric amounts of moles reacted, or of reactants. Okay? And so I really want to emphasize this, so I'm actually going to write it out one more time. So anytime you see delta H of R reported in the book, or anytime that you calculate it, it's going to be based on stoichiometric quantities that react. Quantities of reactants, and also the stoichiometric quantities of the products that are formed, and products. All right. And so I can imagine this is somewhat of a confusing statement, so I'm going to go through to at least help you visualize this a little bit better. I'm going to write the enthalpy of reaction for the chemical reaction number 1 like this. Okay? So I said that when methane combusts with oxygen, negative 890.3 kilojoules are released. Okay? But the way you should think about it is that this much energy is released every time 1 mole of methane is reacted. Or you could think of it like this much energy is released when 2 moles of oxygen are reacted. Or you could think of it like this much energy is released when 1 mole of carbon dioxide is formed or produced. Or you could think of it like this much energy is released when 2 moles of water are produced. Okay? And so once again, the delta H of R is based on the stoichiometric amounts that react for this reaction. Okay? And so based on this principle, let's kind of test it even further. All right? And so what I'm going to do now is write another chemical reaction. And so I want you to think about this. So what happens if the reaction is written like this? And so I'm going to say we have chemical reaction number 2. And in this reaction, what we have are 2 moles of methane gas reacting with 4 moles of oxygen gas, and this yields 2 moles of carbon dioxide gas and also 4 moles of liquid water. Okay? And so based on how this chemical reaction is written, what do you think the enthalpy of reaction is going to be? So what I want you to do is pause the video right here and think about what delta H of R is going to be. Okay, let's figure out what delta HR2 is going to be. So I hope you notice that chemical reaction 2 is basically just twice chemical reaction 1. So 2 is double 1. And as I said before, the enthalpy reaction is based on the stoichiometric amounts of reactants that react or products that form. And so if the moles of reactants that react and products that form what that means is we're also going to double the enthalpy of reaction. And so our delta HR2 is just going to be equal to 2 times delta HR1, which is going to be equal to negative 1780.6 kilojoules. And so the way to visualize it is that this much energy is released when 2 moles of methane react, or this much energy is released when 4 moles of oxygen react, or this much energy is released when 2 moles of CO2 are formed, and this much energy is released when 4 moles of water form. And so essentially the way you should think about this is if more stuff reacts / is produced, then your delta H of R is going to be bigger. So we looked at how the stoichiometric amounts in the chemical reaction formula affect delta H of R. Let's now look at how the phases affect delta H of R. And so what I want you to think of now is what happens when I write the chemical reaction like this. Is written like this. And so I'm going to write chemical reaction number 3. And in this chemical reaction, what we have is 1 mole of methane gas reacts with 2 moles of oxygen gas, and this yields 1 mole of carbon dioxide gas and 2 moles of water as a gas. And so when the chemical formula is written like this, what is the enthalpy of reaction? And so at this point, I want you to pause the video and try and think of what the enthalpy of reaction is going to be. Okay, let's figure out what delta HR3 is going to be. So if you closely inspect reaction 3, you'll notice that it's almost identical to reaction 1. The only difference is that in reaction 3, the water that's formed is a gas, while in reaction 1, it was a liquid. The water was a liquid. And so if we want to calculate, or the relationship between the enthalpy reaction for reaction 3, between this and delta HR1, is that delta HR3 has to account for the enthalpy, or the energy that needs to be put into the system in order to turn the water from a liquid into a gas. And so the way we account for that is by including the enthalpy of vaporization for water at 25 degrees Celsius, which is the temperature that the reaction is taking place. And so if we take delta HR1 and add on 2 times HVAP at 25 degrees C, what we get is 802.3 kilojoules. Of course, once again, this is the amount of energy that's released when 1 mole of methane is reacted, and also the amount of energy that's released when 2 moles of gaseous water is formed. All right? And so depending on how the chemical reaction is written, that's going to affect what the value of the enthalpy of reaction is. Okay, and so we focused a lot on how the chemical reaction affects delta H of R, but let's talk about the actual value itself. And so far, at least for the three reactions we've talked about already, all these delta HR values are negative, right? And so what I want to talk about now is how the sign of delta H of R, that's going to give us information, and it will tell us whether the reaction at hand is exothermic or endothermic. So delta H of R determines if reaction is exothermic or endothermic. Endothermic. Okay? So you may have heard these terms before in, general chemistry too, but I want to redefine them here. And so the term exothermic, it's a Greek word. And so what it means is that your overall reaction, or the energy transfer of your overall reaction, results in energy being released from the system. And so overall reaction releases energy from system. To paint a clearer picture of what exothermic means, I want to draw for you a plot. And so in this plot, the y-axis is going to be the enthalpy of the system. And on the x-axis, I'm going to draw what I'll call the reaction progression. Or you could think of it like a timer. So what happens as the time for the reaction keeps increasing. Okay? And so at early times, what we have are mostly reactants, right? So at the beginning, we start with just reactants. And let's say they're at some sort of enthalpy value. And so if our reaction is exothermic, what that means is that as the reaction proceeds and we start forming products, that those products are going to have a lower enthalpy value than the reactants. And so our delta H of R, which characterizes the net energy transfer of the system throughout the process, that means if our products have a lower enthalpy than the reactants, that our delta H of R is going to be less than 0 or negative. And so this is what happens when the net overall reaction is exothermic. Now, in contrast to that, we could have a reaction that's endothermic. And so what this means is that the overall reaction actually consumes energy or absorbs energy. And so if we draw the same plot that we drew previously, so if we have the enthalpy of the system and the reaction progression or reaction timer, and our reactants start with some value of the enthalpy. As the reaction proceeds and we form products, those products are going to have a higher enthalpy value than the reactants. And so our delta H of R is going to be positive or greater than 0. All right? And so anytime you see delta H of R, you need to pay attention to the sign, because that's going to tell you, whether energy is going to be released from your system and you have to worry about, what to do with that energy, or if energy is going to be withdrawn from your system and you have to figure out how to feed more energy into your reaction to keep it going. All right? Now, as I mentioned before, the enthalpy of reaction, it's defined for if stoichiometric amounts of reactants completely react to form the products. But now let's think about what happens if in your reaction not all of your reactants are consumed. So let's think about what happens if reactants are not completely consumed. So let's think about what happens. Let's think about how do you actually calculate the delta H of R for your system, or the enthalpy change for your system, when not all of the reactants completely react. Basically what you do, if you want to calculate the enthalpy change, what you're going to do is you're just going to take your delta H of R value for some temperature and some pressure, and to calculate the enthalpy change, you're going to multiply that delta H of R by the extent of reaction. And so if you remember from chapter 4, your extent of reaction, your little Cassie guy here, this Cassie guy basically describes how many times a reaction occurs. Okay? And so I'll write that here just as a reminder. So you could think of it as how many times a reaction occurs. All right? And if you remember from chapter 4, the extent of reaction can be defined in two different ways depending on if your system is a batch system or a continuous system. And so if you have a batch system, your extent of reaction is going to be the difference between the final amount of moles for some species minus the initial amount that's in the system. And that's going to be divided by the stoichiometric coefficient for that species in whatever reaction you're looking at. Okay, I'm going to move this down a bit. And continue to draw it here. All right, and so that's the definition for if you have a batch system for the extent of reaction. If you have a continuous system, so if you're looking at molar flow rates, what you're looking at is the molar flow rate of some species out of the system minus the molar flow rate into the system divided by your stoichiometric coefficient rate for that species. Okay? And we'll go over more about how to manipulate or how to calculate this extent of reaction. But what I want to highlight here is that regardless of whether you have a batch system or a continuous system, your extent of reaction is going to be unitless. All right? And so these are the formal definitions for the extent of reaction. And so with this extent of reaction, we're going to use it to calculate the enthalpy change that occurs in a system when there's a reaction going on. And so if we have a closed or a batch system and we want to calculate the enthalpy change due to a reaction, the way we calculate it is we say delta H is going to be equal to the product of our extent of reaction times the delta H of R at some temperature and pressure. And so I call these TR and PR. And so these are just going to be the temperature and pressure where the reaction occurs. All right, so we have a delta H, and we're multiplying it, or it's going to be equal to the product of the extent of reaction times the enthalpy of reaction. And I want to point out here That's, it's an enthalpy change. And so what we're looking at is we have units of energy here. Okay? Now, if we have a open or continuous system, and we want to calculate the enthalpy change, we're going to do basically the same thing, but mathematically it's going to look a little bit different. And so for an open or continuous system, we're going to look at the enthalpy, or the rate of the enthalpy change, so delta H dot. And this is going to be equal to our extent of reaction times our delta HR. But we're also going to multiply it by this term in brackets, which is equal to the ratio of our stoichiometric coefficient for that species that reacts, for some species that reacts, times the stoichiometric coefficient rate. Okay? And the reason we write this, you'll see in the book they go through the formal definition of it, but the reason we write this is we want to get the units to match, right? So on the left-hand side, we have a delta H dot, right? So that means we're looking at an energy per time, right? But the product of the extent of reaction and delta H of R just gives us energy, like we see for the closed system. And so if we want to get that per time unit, we basically have to take this, multiply that by this ratio here in brackets. And that's because the stoichiometric coefficient we have here has units of moles, and our stoichiometric coefficient rate has units of moles per time. Now, this may seem confusing, but the nice thing here is that this term here in brackets is just equal, or has a magnitude of 1. And it gives you units per time. That's all we want out of it. And so the way to think of it is that if we take our delta H of R and we multiply it by this term in brackets, we could just call this a delta H of R dot. All right? And so when we actually write out the change in enthalpy rate, or delta H dot, what we're really multiplying it by is just the extent of reaction times this delta HR dot. And so algebraically it looks a bit confusing, but when you actually punch in the numbers and calculate it, it's the same as it would be for the closed or the batch system. But now what we have are units of energy per time. All right? And so that's how, the reason we're doing this is because remember, we have to figure out what our change in enthalpy is if the reactants we feed into the system, not all of them are completely consumed. All right, so that's why we're multiplying delta H of R times this extent of reaction. Okay? A couple more things I want to define for you is that typically what you'll see in the book is not just an enthalpy reaction for random temperatures. You'll actually, what's typically reported is something called a standard enthalpy reaction. And it will be symbolized by this delta H of R with a degree symbol there. And so what that means is, or when you see it reported, it's just going to be the enthalpy of reaction for some reaction at some reference temperature and reference pressure. And the way I'm going to write it in the lecture notes is T of R and P of R. In the book, though, you'll see it as, okay, so I'll write here, it's T of R and P of R in lecture notes. In the book, you'll see it written as T naught and P naught. And typically, in the book, T naught is equal to 25 degrees Celsius, and P naught is equal to 1 atmosphere. Alright, so typically in the book, you'll just see 25C and 1 ATM used as the reference conditions for your reactions. But of course, you could use any sort of temperature or pressure for your reference. That's just going, because ultimately, because enthalpy is a state variable, it shouldn't affect what the delta H is going to be, right? Because you're looking at the changes of enthalpy.